I thought that it's about time to step back and have like a synoptic opinion or statement of what is the status of gravity theory and gravity control technology. So I was planning to refer rather to some advancements which are not as well known by the various audiences regarding gravity research, and then maybe a little bit unexpected to start engage the audience, the readers, the viewers, not necessarily those online right now, but those who might read these slides later on to to help. And for the typos here and there, it's very important to get away from the trap of doing research and development without looking what others are doing. And then many independent researchers would pull in different directions, and we won't ensure a coherent advance in this area. But about this a little bit more later. And still, actually, in connection with this, there is a need to help mainstream science. Physics is somewhat stuck in the 1970s version of the standard model, and it's not easy to, first of all, it's not possible to include the various alternative theories as being too separate from the standard model. So we have to start looking at how to connect with the standard model and how to glue or rather integrate our theoretical developments in at least in the language of the standard model. And last part, help with the gravity control technology. The point is the stage by now shifted in the area of developing the technology of gravity control. But that means solid state physics, means two-dimensional materials, engineering, and those are areas where those who started the theories and understood the experiments and so on do not have an expertise. So it's clear that by now we need to form teams to develop such a complex, extensive subject. So gravity research, and at this point I might say the real breakthroughs happened with Frederick Alzofon in the 1980s, and essentially has almost nothing to do with general relativity and physics, physics of gravity prior to that. Also because this breakthrough developed or engaged the research in the area of elementary particle physics, therefore in the turf, if you want, of the standard model. Now, the standard model, it's an amazing achievement of physics, theory, technology, teamwork, and all that. But they systematically disregard gravity as saying, well, it's too weak to be measured, therefore we are not studying it, on one hand. On the other hand that's explained so beautifully by Einstein's general relativity. Therefore, it's applied to cosmology, to astronomy, and we won't get into that area. It's their turf. We do the lab and particle accelerator developments. But this is a very important point to emphasize. Pause a little bit if you want. Science is very much fragmented because of the way it was developed by individual researchers, by individual types of experiments which focus on some particular type of phenomena, and then the need of unification is obvious, and progress goes in that direction. One of the fundamental of the best examples is unifying, say, electricity and magnetism, Faraday, Maxwell, and so on. On the other hand, back to standard models, one in elementary particle physics and the other one in cosmology, because I would rather think of general relativity as a standard model in cosmology. Those two are very much separated, and there is a movement, so-called quantizing general relativity. But that's essentially a wrong way to try to save, say, general relativity. And there are, of course, there are many things to be said about that, but maybe not right now. So again, separation led to this dichotomy. Elementary particles, we have the standard model, and then cosmology, we have general relativity. Back to the breakthrough. Frederick Alzofon, who, first of all, was a professional physicist working in a very big laboratory with particle physics, with nuclear physics, with anyway the analog of Fermilab, but I don't remember exactly which lab he was working on at that time in the 60s. Had an intuition that gravity has to do somehow with the polarization of what he thought at that time is some vacuum fluctuations, positron electron pairs, and the free energy type of thinking. He then tried to get a better understanding. I mean, he also knew about UFOs and so on. Anyway, the story is really exciting, and I encourage you to read the book written by his son, David Alzofon. He has two sons, David and Daniel, another physicist. Anyway, so to read his book, or at least this part of that book, documenting Frederick Alzofon work, called Gravity Control with Today's Technology. I think I'm close to what the real title is. To learn more about the history behind his breakthrough. At this point, I would like to make a correction. So he advanced an effective theory for gravity, which is not really what's going on. But more importantly, he performed the experiments which verified that by dynamical nuclear orientation of the nuclear spin, one can modify the weight of a body in Earth's gravitational field. Now, that's the experimental part which demonstrates that the core idea is correct, and that gravity is really a byproduct of nuclear structure, nuclear force, and belongs to the realm of elementary particle physics as a theory. Later on in the 2000 and something, let's say 5, 10, I started to understand clearly that the quark structure with their fractional electric charge obviously is the candidate for a perturbation of the electrical interaction between two particles, like neutrons, for instance. Two neutrons, total charge 0, viewed in this way, they're not supposed to attract each other electrically. But when you consider those fractional charges, then it's almost clear that changing the spin direction of each might affect how the three fractional charges, called quarks, of one neutron will interact with the three others of the other neutron. So I started to write and explain this and coined that gravity is just the polarization of nuclear spin. And then after setting foundations of gravity based on the standard model of quark structure, I came across Alzofon's work through David Alzofon's book, confirming clearly that this is indeed the case through his experiments. That's why I decided to call this the Alzofon-Ionescu theory. And you can find the articles where I explain it in the Vikstra archive. There are links contained in this slide presentation, and I will not go over like a tutorial of the corresponding theory in today with my presentation. Also, compared to the previous presentation, beautiful presentation and with a lot of mathematics, it's not, you don't need to understand mathematics to know general relativity to understand these basic ideas. At the conceptual level, that gravity is a consequence or a byproduct of a polarization of nuclear spin. And then just start looking at the experimental proof of this. And this is exactly what Alzofon did. And at this stage, I would also emphasize this theory. It's so elementary and so natural that several others came with this connection between gravity and nuclear force. One of them, which I learned recently about, is Kai Darmos, who has a compilation of experiments demonstrating that gravitational constant, the so-called big G, is material dependent. And more than that, by studying the corresponding dependency, one can almost immediately come up with a linear equation proportionality between gravitational force or gravitational constant and the number of nucleons of the corresponding element. Again, this is, I would say, at the level of a high school lab experiment. Once you have the data and you analyze it, you can come with like a Hooke's law or proportionality between G and the number of nucleons of the corresponding chemical element. And maybe I should show this at this point. The picture is taken from the interview of Sky Demos took by Robert Sheldrake, or Rupert Sheldrake. I encourage you to watch that interview and get all the information behind what I mentioned earlier in brief. So back to the fact that the theory of gravity is really simple once you understand that there is a quark model behind it, that they have fractional electric charges, and then that electric force is really just the divergence part, or let's say it's the part of the force of a field which has a divergence. So this is explained in Sky Darmo's work. He has a so-called complete guide to quantum gravity. Now, it's by far not complete, but well, we all tend to exaggerate a little bit. But what I also avoid is to call such a theory quantum gravity, because the term is very much reserved to another type of theories which try to quantize general relativity. And I'll come back to this later on. So there is no, the main point here is there is no need to quantize general relativity, a theory that was written more than 100 years ago with a language which is 200 years old, differential geometry, Riemannian geometry, and not, first of all, use what we already have, the standard model. And also, when writing a theory, one should write it in quantum framework from the beginning. No more continuous space-time and the old languages of differential geometry and so on. Again, as a quick recap, Frederick Alzofon effective theory based on quantum fluctuations of the vacuum is an effective theory, but it's not the true origin of gravity. On the other hand, the true origin of gravity anybody can understand once learning about the quark structure, which is usually neglected by any, let's say, high school level introduction into physics and matter. And they talk about electrons, protons, nucleus, atoms, and they stop at that level without giving like another one or two lectures that these protons and neutrons do have a structure, the quark structure. So at this point, it's clear that we need also to advocate some simple changes, updates in the educational system. So enough of that for now. Then again, about research on gravity, there is a plethora of peer-reviewed articles relating gravity and nuclear force. So the researchers are aware of that. How many articles? I would say more than hundreds. But you need to use an AI to do the search for you. And more importantly, you have to be open to learn in parallel to developing your own theory. Then there are many peer-reviewed articles studying nuclear spin-to-spin interactions, which are part of the Standard Model, part of the Lagrangian of the Standard Model. So this term is clearly pointing towards an explanation of gravity in terms of the nuclear force. But these peer-review articles are written by physicists who work using the Standard Model, which again ignores ab initio gravity is not having to do anything with fundamental forces. So at this stage, it's clear that we have all the material needed, theoretical, to establish gravity, part of the Standard Model. In fact, the theory is already developed there, but nobody calls it or relates it to gravity. So regarding this anomalous gravitational constant findings, most of research relating or in connection with gravity, mainstream research, also using general relativity, tends to consider that there is such a thing as the gravitational constant. It turns out that, again, there are plethora of experiments and articles which document that the measured gravitational constant is by far not within the experimental errors. But these articles are, again like implicitly ignored, and nobody really pauses for a moment and questions if the theory we are developing, it's really scientifically correct. I mean, since so many articles document that it's not a constant, then at some point we should stop claiming that it is. Now, why it's not a constant? Because gravity is an average of polarization of nuclear spin corresponding to the divergence part of the hydrogen atom, unified field. At this point, I would like to mention that in the previous talk it was mentioned, well, gravity's permittivity coefficient. Indeed, that's what it is. First of all, the proton is not a separate entity from the electron. this is how we develop the theories. Theory of the electron on one side, theory of the proton on the other side. But no particle, whether electron or proton or neutron, first of all, comes just with an electric charge or with a magnetic moment. All particles come with both aspects, which show clearly that the field, whatever field that is, has a divergence part and a curl part. Of course, this is well known in mathematics. Any field can be decomposed in such two parts, with divergence and with curl only. That's called Helmholtz theorem. But it's not just the math, it's the physics nowadays that any particle will also, with or without electric charge, and by the way, no matter particle doesn't have electric charge. The neutron is not neutral. And now if you might think, well, what about photons? But those are bosons. Those are a totally different thing. So all matter particles, fermions, have electric and magnetic charge. Now, what's called magnetic charge is not what you expect in the Maxwell's equations. The electric field and magnetic field B are really curvatures, are forces. They are not really the sources underlying those forces. They are not the sources of those. So there is such a thing as a magnetic charge, and it's called and it's quantized, and it's called a fluxon, and it's at the level of the electromagnetic vector potential, really. Without going into details, coming back to this level, the hydrogen atom is a unity of quantum object, of unity of matter, and the electron is not a separated thing from the proton. So there is a much more at length explanation of this unification of electron and quarks, where the electron is really the fourth quark, and the usual quarks are really space-like quarks, three of them, which these explanations or this unification is explained in my articles available on Vixra and so on. Learning at the top level about these advancements, unifications, gives a much better perspective in which direction to develop the current theories. So, and it doesn't take much time. I mean, learning about this unification of electron and quarks could take 2-3 hours of reading. So back to the gravitational constant. Dozens of articles report the experimental determination of gravitational constant does not fit the standard value of and standard deviation corresponding to the measurement errors. So I said community, those interested, readers, viewers, and so on, those some of those, of course, are just enjoying learning from presentations, if you want. But on the other hand, writing a report, it's a lot of fun, and gives much more satisfaction. At this point, I would say, think of watching Zumba or work or Zumba dance and not trying it yourself. It's really the same thing. Or watching how others are training in the gym and just watching. So I'll state it as a homework. Write a report or article documenting these sources and articles. For example, even Sky Dermos articles are not really enough, let's say, not polished, but structured to become some articles you might want to use as a reference to direct towards the original sources of experiments which document that gravitational constant is material dependent. So as a partial conclusion for now, gravity is an electric type of force due to the spin polarization of nucleons and averaging to a weak force from the strong nuclear force in the quark model of the standard model. I want to emphasize again that this is so clear that it's just a matter of bringing it to a larger public. At this point, there was an attempt, a very solid development of the theory by Abdus Salam and collaborators. And I recall that Salam was one of a co-author of the electroweak theory. And in the, I recall, like 70s or 80s, he formulated a strong gravity theory, explaining gravity as a byproduct of nuclear force. So this was already done in the maybe 70s. But how is it possible for such a breakthrough to be completely ignored or forgotten? Well, that's a different story. So strong gravity is really the technical theory developed on top of the of the standard model, which I would probably have to look into more detail to see how it can be connected with the intuitive picture which everybody gets, that gravity is really a nuclear spin polarization effect. The problem with incorporating that direction of research is that it's probably formulated in terms of differential geometry, gauge theory language, which is, I would say, not outdated, but no longer necessary to formulate a theory of gravity as a polarization of nuclear spin. So let's retain this early theoretical development by Salam of strong gravity and go back to the Alzofon core finding. which is the experimental result. Dynamically polarizing the nuclear spin results in a change in the weight. Now, if you look at the whole story, with which is, as I said, explained by David Alzofon in the book, this is a very solid example of applying the scientific method. First, you start with the observation, which gives you some ideas of what's going on. Then you formulate a theory, and then you verify it experimentally. The observation part is kind of cheating a little bit, because Alzofon used some data available from Air Force chasing a UFO and so on. So again, I'll let you read the full story in the book by David. Also, mentioning this kind of observation, which is really cheating, looking at how others did control gravity, is very difficult to sell in scientific publications. So that somehow has to be omitted, and we have to do the work ourselves and develop the theory and redo the experiments. At this point, Mark Sokol and at Falcon Labs is working and doing, it's working a lot in trying to replicate Alzofon's experiments. So that's a good source of information regarding that level of development. But taking into account that this is already well taken care of, the origin of gravity, the experimental proof, I thought it's time to go beyond the experimental stage to what I call the technological phase of implementation. So I started to learn about advanced materials, solid-state physics, and so on, and presented some key points to be investigated by the engineers who design and manufacture new materials, and how this connects with controlling gravity. This is explained in a presentation, ROCAM, so Romania Conference on Advanced Materials 24. Then there are many more detailed explanations in the Tesla Extraordinary Conference 2025. So I encourage, if you're interested, there you have it. And back to this important point, how you may choose to help. And this involves not just the readers and viewers, but also the researchers, to learn a little bit more what it's already known, and then continue this cycle of research and development, and then disseminating and teaching, and then helping others, which is what's called service to the profession. And as a professor, by now I realized how important it is to mix all these things: teaching, teaching, research, and service. And I usually think research, teaching, and service, but it depends on the on a case-by-case interest and so on. So let's take a look at research and development, the mainstream versus independent research. At this point, as a general culture, if we're doing science, I would say that the book by Thomas Kuhn, The Structures of Scientific Revolutions, is a must, but not to read because it took me quite like a week or so to read it, browsing and so on, extracting the essentials. And if you're interested in just a brief synopsis, there is a recent presentation to a history of science meeting that I went and presented, where we see some key ideas, among which are the following. Science paradigms evolve similar to biological species and have a lot in common with politics. And I'll leave it at that. But what do we take from this? That we need to collaborate. We need to establish groups of researchers having common goals and supporting essentially the same theory, which starts to resemble to how political parties are. What's the function of a political party and so on. So too much fragmentation of research into independent researchers going in various directions will not have the same impact as in the case where we try to build teams working on a certain direction, certain theory. Well, at this point, I should, of course, recognize that we love to do research, and being so much fun, we kind of like to be left alone and do our developments, and it's natural and there's nothing wrong with that. But again, is it possible to engage a little bit of service to the profession? Well, we'll see. So, on the other hand, developing a theory which is almost completely detached from a mainstream scientific theory, like the Standard Model or general relativity, has a lot of drawbacks. And to advance science overall, one needs to do a research and development which is compliant with some mainstream science. So, bottom line, I feel like I'm preaching here, but from just research and development to go to learn, research, develop and disseminate, then teach and service. And of course, refining such denominations is something we see going on in various directions. So it's normal to see a more complex structure, and including in how our activity is structured. then of course I have some suggestions for research and development that would help. And here is my apology. So studying such exciting topics and novel approaches is tempting. Yes, it is, because it is the journey, not just the destination. So we all understand that. Each of us with our own journey. But there is a need to collaborate and contribute to other researchers' work to achieve a consistent new theory rather than scattered, author-dependent formulation, etc., etc. And let's come back to some more technical material. Developing the theory of gravity in balance or in consistency with the standard model of elementary particle physics. That would upgrade and mark a new level of this standard model, which is stagnating significantly since the 1970s, after the Higgs boson was found and so on. And at the same time, if broadening the range of phenomena one considers, in order to compensate the separation of theories due to separation of experimental approaches, then one should learn a little bit more in neighboring sciences. For example, the physicists to learn more chemistry and biology. And I would say mathematics is comes later on, when you really need to implement it in a formal way. And although some mathematical frameworks can help from the beginning to know how to think about the corresponding unifications, it doesn't have to be, mathematics doesn't have to come first. It's not the equation that matters. And now I recall hearing Mikio Kaku saying, I want to know the equation which rules the universe. No, it's not the equation that matters, but rather top-down principles and what's usually called the conceptual interface of a theory. And speaking of principles, Pythagoreans, got it more than 2,000 years ago. Number rules the universe. So Zeno, with the indivisibility of infinite indivisibility of action, of motion, already got the idea of quantum of action and so on. Much more to be said, that the ancients had quite important ideas and, if you want, philosophical understanding of how the universe works. So it's not the equation. What is needed, and it's already done in considerable amount by my research in the articles I already made available, I'd say published, but not peer-reviewed, is a conceptual, reformulating the conceptual foundations of the standard model. And here I just included a few important ones. First of all, there is no such thing as space-time continuum. Not a continuum, and there is space and time are not really physical concepts, but rather emergent and mathematically formulated concepts. What establishes clearly in the science of the 21st century is the use of the network model. It's so everywhere that it's somehow amazing that we're not learning from this lesson to downplay the idea of space and time. Then upgrading the role of Feynman diagrams and the higher version of quark line diagrams. One should look at the developments in quantum computing and quantum computing hardware, where you see clearly that we are building some networks which process quantum information. And this, of course, reflects that in nature, because we are essentially copying and looking at how nature does it, and then we try to replicate it in ourselves. So nature is just networks and communication, and nothing to do with space and time. Space comes from our habit of measuring distances between objects, geometry, ancient geometry, Euclidean, and so on. Of course, you want to know when you buy a couch, you measure the door. Will it fit through the door, and so on? So it's so practically oriented that it's ingrained very deeply in our minds, and we think that space is something real. No, it is not. Time also. Clocks are made exactly to create time. And Einstein said, well, the illusion of time. So he had also an understanding of this. But we don't have enough time here, nor the purpose of this talk is to mention this. But if you're interested, go to articles and read about how the space and time emerges from the quantum computing flow of Heraclitus, who said, Pantare, everything flows. There is only the change. So how does stability of objects and what we think reality is stable emerges from the flow? I preliminarily explained it in one of those articles. Another misconception, starting with the 1950s, is that quarks are particles. No, quarks are not particles, but rather principal directions of the field of an hydrogen atom. Think of pictorially that there are like three tornadoes emerging from, say, a proton or neutron. And the problem is the electron is a fourth quark, but at the present time it's not clear how to take those three tornadoes to close them and generate a reasonable technical model of the hydrogen atom, which also upgrades the electronic orbitals models already in use. What is clear is the so-called Hopf vibration is essential for that. And again, I give some hints here and there in some articles. But bottom line, without the technicalities and the need for peer-reviewed new model of the hydrogen atom, we can retain the natural, almost obvious fact that quarks are not particles, are directions. And they have a spin of those tornadoes. Spin is everywhere in quantum physics. It's associated with helicity and all that. Then another important unification of atomic and nuclear is this important new breakthrough that the electron is really a fourth generator, which is time-like. What it really generates is the quantum phase, like a clock attached to the atom. A clock that, it's almost obvious, is what Einstein said about any coordinate system. You have to have a clock and you have to synchronize two such coordinate systems, reference frames, in order to make sense of the idea of time. So this quantum phase, it's really a proper relativistic quantum order parameter, which is also intuitively explained by Feynman in his QED book, saying that any particle carries like a tiny clock with which measures time, and it's related to the quantum phase by the formula exponential of EI omega t. So this was already understood in the 70s, the relation between quantum phase and time. But now it became quite clear, almost obvious, that there is no such thing as a linear time, and the only order parameter, it's a proper order parameter. Each particle has it, each matter particle has it, and it's abstractly called quantum phase. Then an intuitive image is that the universe looks three-dimensional because of those three quark directions. But then there is no fourth dimension as a time dimension, but rather that each matter particle has a vibration aspect, a periodic change, which you could call it vibration, which justifies again an intuition of another famous researcher, Tesla, who said, if you want to understand the universe, look in terms of vibration and energy. These are lessons who should not be forgotten, and when developing a theory, one should look at what these giants said before us and not disregard that. So what about the technological advancements, or rather, what's the technological level for the research in gravity control? And here I'll just point to the highlights, point to the stages. First of them, again, 1970s with Alzofon. Let's say we need to perfect the methodology of nuclear spin polarization. That's also referred to as dynamical spin polarization in the theory of Alzofon and his experiments. It's quite widely used in nuclear magnetic resonance, measuring chemical shifts and analyzing materials. Also in magnetic resonance imaging. So we have not just the technology, but the whole infrastructure is so well developed, except nobody thought it might connect with gravity in some way. But then there is the other part. Higher temperature means separation, decoherence, gases, Brownian motion, and so on. So you want to avoid such phenomena because then you cannot align the spins, really. So then you need to include what aligns the spin. First of all is rotation, which anybody who played with a gyro clearly understands. If you want to maintain an axis, then you have to spin the object. Then the second is supraconductibility. So if you want to have a phenomenon without friction and decoherence, loss of properties, and so on, then one has to lower the temperature at the level of supraconductibility. Then look at the papers by Tashmar, work by Pokletnov, Ning Li, and so on. But then there is the next level, which is really new. There are lots of achievements in quantum computing hardware and two, material science and design. Quantum computing reached the level of manipulating individual nuclear spin, which means we can orient the spins, nuclear spins, one by one. Now, that technology exists, so how can we use it in connection with gravity control? And then learn about these two-dimensional nanomaterials, which have amazing properties precisely because they are already polarized in 2 dimensions. So you have covalent bonds in 2 dimensions, and then the third one is automatically polarized perpendicularly to the corresponding surface. So I think I give you the synoptic view of what is the status of gravity control, gravity theory and control and technology. And it involves a lot of learning of what is already documented and published in articles, and then try to help developing this new this direction from the level it is already. So with this, I'll just leave this slide on, and feel free to share the PowerPoint presentation. I think it's about time to stop.